Welcome everyone listening on YouTube. So this is our 19th live stream geometry session. So today I took problems from the contest Mathley. So it's sort of like an online contest in Vietnam. And all the problems I took were from the years 2011 and 2012. So it's a really nice contest. So I hope you all enjoy these problems. So let's jump into it. All right. All right, so here's the first problem. You guys all see it? All right, so I try to sort them from sort of easiest to hardest. So we have a circle with center O. Right? And hi, Rom. Thanks for joining.
Hi.
All right. So just a sec. So are you Ram Swaroop or Ramakrishna Sen or someone else?
I'm Ram Swaroop.
All right. Yeah, you just spoke really quickly, so I couldn't tell. That's all right. All right. So we're going to draw the two tangents to the circle. And this should be point A. And B and C are the tangents. Just gonna do this. Q is a point inside the angle BAC. All right. This is point Q. P is the perpendicular to AQ from O. I think this might be a fast one. Yeah, I try to sort them easiest to hardest. Let's see. That should be point P. All right. And then we draw the circumcircle of BPQ and CPQ. So I'm going to hide those to this line. It's the circumcircle of BPQ and CPQ. And, oh, actually, I don't want to hide line OP, at least not yet. So OP meets the circles at I and J. So I'm just going to relabel them I and J. And we want to show that OI is equal to OJ. All right, so I'm going to draw segment IJ. And that should be it. Maybe I'll just draw BP and CP. All right. So yeah, Q can really be any point within the angle BAC. It feels like power of a point, right? Because OP times OI is the power of O with respect to that circle, and OP times OJ is the power with respect to that circle. So we want to show O has the same power with respect to both circles.
AIQJ cyclic means something like AO is the median and AQ turns semi-median. So might not be cyclic.
Whoops. So no. AIQJ. I keep clicking the wrong thing. AIQJ isn't cyclic, but maybe there's Oh. Interesting idea though. Let's try IQJ. Maybe it's worth drawing the centers of those circles. I'm not sure if it'll do anything. I'm just trying it out. Okay, so we want to show O has the same power maybe we could use Casey's theorem. So the difference between the powers of O with respect to those two circles is, actually, I'm not sure about Casey's theorem. But we know OP is parallel to DE, right? In fact, I think we kind of have a mid segment here, right? Yeah, so basically, we know D is the midpoint of IQ and E is the midpoint of JQ. And
isn't DOE cyclic? This is just the 9 of QIJ.
DPOE. Yeah, it's the 9-point circle. Yeah, we want to show that that's the 9-point circle, right? DPOE.
Yeah, DP come from definition of 9-point. We just want to show that they are cyclic.
So yeah, DP and E is the 9-point circle, right?
Yeah.
And so we want to show that O lies on that 9-point circle.
Yes.
Maybe that's, let's see.
Yeah, we also have parallel conditions, so should be easy.
Did you say you have a solution or you have an idea how to solve it?
Or maybe DO parallel to, yeah, DO is also parallel to QJ. We can also try proving that.
Yeah, let's see if we can prove DO is parallel to QJ.
We are missing the facts that B and C and that tangent thing.
Yeah, we have to use that. Those are tangents, right? We haven't used that yet.
Oh, by the way, ABPOC is cyclic because angle OPA equal to angle OBA equal to OCA. All are 90 degrees.
OPA is, oh yeah, ABPOC is cyclic.
This might help.
That might be the key. Let's see. All right. Feel like we're close.
I think the rest is just angle chasing now that we can chase down IPD and PJQ to show them same.
IPD and PJQ and what are the angles you said? IPD is one of them, right?
Yeah, we just want to show that DP is parallel to QJ or some. That would automatically imply that PO DE is cyclic. Yeah, I mean DO should be parallel to QJ.
So yeah, how do we prove DO is parallel to QJ? It's still not obvious to me. So yeah, we want to show DO is parallel to QJ, right? It feels like an angle chase, but yeah, I don't see immediately how to do it.
Yeah, let me try this with some pen and paper.
Okay. think, yeah, so, yeah, we want to use that, this is cyclic. So the power of I with respect to that circle is IP times IO. And the power of J with respect to that circle is JP times JO. So if you add the two, it's, let's see. So is AO a dot? Oh, I'm sorry, go on.
Yeah, so the circle centered at D and D has radical axis PQ. So how can O have similar powers to both?
Oh,
I think there. Yeah.
No, it does. So the radical axe. So the it's really weird. The power of a point with respect to two circles can be the negative. Basically, the power of O with respect to one circle is -1 times the power of O with respect to the other. So they have the same absolute value, but they're negative. So that's why O doesn't lie on the line PQ.
Okay.
Yeah, I've actually seen a lot of people ask that same question, and I got tricked by it a couple times too. It's so weird, but yeah, it's -1 times the power. Is AO a diameter of yeah, so O is like always the same point, right? Well, yeah, okay. So yeah, we want to use kind of that AO as a diameter, right? So OB is equal to OC, and we want to show OI is equal to OJ. All right. So yeah, can we show DO is parallel to QJ? It's kind of the same as showing DO is perpendicular to AO, right? Well, no, not necessarily. This is tricky. Let's see. So if we move Q along the same ray, does the figure just sort of stay? Yeah, there's a lot of flexibility in this configuration. I mean, Q could be any point, right? Let's see if there's another circle. I think I'm going to try this. Let's see. Is OC tangent to that circle? Actually, I don't think it is. No, not necessarily. It feels like an easy problem, but yeah, it's not that easy, I guess.
Maybe we can try proving that dP is equal to OE.
dP is equal to OE. Yeah.
Because cyclic, so it should be equal. dP is chaseable, but OE, I don't see a way to track OE.
Yeah, basically we want to show dPoE is an isosceles trapezoid, right?
Yeah.
I still like trying to show the powers of O with respect to both circles are equal. Is there some other circle, like for example, I draw that and I draw that. See if this helps. Not really. Oops. So we want to show AO as the median of this triangle.
I think we should maybe extend something here. Yeah, because D and D don't seem related somewhere. Maybe try extending AB and AC.
Extend AB.
And AC. Let them meet the other circles, and seems like that line is collinear with Q.
Okay.
Looks like collinear.
Let's see. Yeah.
It's
all right.
And to exploit symmetry, we can also add the perpendicular. We can extend AO to meet this segment at some point. Yeah, but first we need to prove that Q lies on this segment.
Yeah. Okay. All right. Let me hide some things. That seems like a good observation. Butterfly theorem. Ah, nice. Write your solution. I'm curious. All right, so to show Q, oh, that's just Mikkel's theorem that F, Q, and G are collinear, right?
That's just Mikkel.
Yeah. And then once we know Mikkel's theorem, is IFGJ cyclic? I don't think so.
Yeah, I was saying that extend AO to meet FG at R. We get a symmetry and also a cyclic quadrilateral DOQR.
Is AFG, AFG, is that isosceles? I think it is. I think A.
Yeah, A lies on the radical axis, so AB times AF is equal to AC times AG, and we know that AB.
I see. So yeah, basically AFG is isosceles, and AO is the angle bisector of BAC, right? So AH is perpendicular to FT, right?
I think we can angle change this now. Or
and now
yeah, IF should be parallel to GJ because both of them are 90 degrees. I mean, IFQ is 90 and JGQ is also 90.
JA. Say that one more time. I'm sorry, I missed it.
Yeah, I mean, IFQ is 90.
Okay.
And JGQ is also 90. So
right.
IF should be to GJ.
Ah.
And
so,
here we are H is
yeah,
the midpoint. O should be also be the midpoint.
So yeah, that solves it. Okay. So I'm gonna write that out. Hold on just a sec. So yeah, let me delete some of the stuff I added. And I'm gonna add it back. I'm not sure if they're coming. Yeah, maybe I'll ask them later. But yeah, I don't know. All right, so all right. Okay, so oh wait, we want points I and J. We just don't. Okay. All right, so that's the first step. All right. And then yeah, I'll do an angle chase basically. It's just Mikkel's theorem, but yeah. FQP is equal to an angle. First I should note that ABOPC is cyclic. So all right. Sorry, I'm typing a little slower today just because one of my fingers has a Band-Aid. So that is slowing me down just a little bit. All right. And then once we have that, angle FQP equals angle PBA is equal to angle PCG, which is 180 minus angle PQG. And so that means F, Q, and G are collinear. All right. Oops, sorry. Let's make some room here. And so we can draw in that segment. And then by power of point, we can show AF equals AG. So and then AB equals AC implies AF is equal to AG. All right. Let's see. And then once we know that, let AO meet FG. So first I'm going to say angle IFQ equals 180 minus, I should say angle, yeah, 180 minus angle IPQ, which is 90. And then similarly, angle JGQ equals 90. Whoops, sorry. There we go. We can draw those in. And so also, that's the proof using the butterfly theorem. You know what? Maybe I'll show both. So once I finish this, I'll show the other proof. So since AO bisects angle BAC, or I'll just say that. That means that AO is perpendicular to FG. since AF is equal to HE. Okay, so if we let AO meet FG at a point H, then FH equals HG, FH equals HG, and all three are parallel, so we have IF is parallel to AH, which is parallel to JG. So that means that OI equals OJ. All right. I like it. So now I'm going to do Raffaello's solution. Because it looks interesting. So this was the first solution. And Raffaello looks like he already LaTeXed the solution. So that will make my life easier. All right. So I'm going to copy it into straight into the LaTeX. Oops. Let me do the lines. Yeah, sorry, I'm just going to take away the color just because I'm not sure how it works in GeoGebra. All right, let's see. All right. So let's see this solution. Let G be the intersection of, so I'm going to delete some of the stuff I added. Thanks for having it already teched up. That's pretty nice. So G is the intersection of B, Q, and O. Okay. And B prime is the antipode of B. Okay, so I'm going to use my reflect tool. So that's B prime. Okay, we mentioned before that ABOPC is cyclic. G lies on PQCJ. So G BQ, not AQ. Oh yeah, okay, my bad. So so it's like G is where those two circles intersect. Is that true? Yeah, okay. So yeah, I'm gonna hide this just so that, okay, so that's G. So G lies on PQ CJ. Is that obvious? Is that kind of just like an angle chase or something? Because, yeah, I think it's an angle chase because we can show angle BGC is equal to angle BPC, right? So let's say by an angle chase. Okay. And so once we know that, angle QGC equals angle BGC. It's AB. Oh, that is the angle chase, basically. Okay. Now, angle QGJ is equal to B GB prime. Let's see. QGJ. So basically, you're saying those points are collinear. Is that obvious that those points are collinear? So, how do you know that G, B prime, and J are collinear? Oh, because angle QPJ is 90, so angle QGJ is 90. Yeah. Oh, you just proved they're collinear. I'm sorry. I just read. You were proving what I was thinking you had already proved. Okay. So G prime is the antipode of G. All right. And so B, I, and G prime are collinear. And then, now we use the butterfly theorem. Okay, so since O is, let's see. So yeah, G, O, and yeah, so we're using the butterfly theorem. On BB prime, GG prime, and this sort of diameter. So O is the midpoint of FH, and then we take those two diameters. I feel like, do we really need the butterfly theorem? Because they're all diameters, right? So it's probably just congruent triangles, right? I mean, we know BG prime BG is a rectangle, right? So we don't even really need the butterfly theorem for that, right? That's just symmetry. But I still like it. It's a nice solution. All right, so I'm going to move to the next one. So ABC is a triangle, and D is the parallel line through A to BC. And we pick a point M on that line. I is the in-center of ABC. K and L are the reflections of M about IB and IC. I'm going to do some reflection here. Well, that's somewhat asymmetric, but okay. So this is K, and this is L, and BK. Whoa, not ML, just L. And BK and CL meet at N. Let me draw. There we go. So I'm just going to draw these points Yeah, point N is like really far away, right? So how do I make this diagram a little? Okay, so this is point N right here. And yeah, I want to make it clear that these are sort of the reflections. So, all right. Okay. NBK and NCL. We want to show AN is tangent to the circumcircle of ABC. Kind of interesting. All right. So MEC is isosceles. MBK is isosceles. Are they similar? Let's see. MCL is 49.4, MBK, no. So we want to show angle NAB is equal to angle ACB. Whoops, sorry. Trying to make it look nice. I'm gonna label these right angles. So that's 90 degrees, and this is 90 degrees. So obviously AEID is cyclic. In fact, we have an orthocenter, right? So MI, is this concurrent on the circle? I think that's just a coincidence. Yeah. Okay. Here we go. It looks like it's concurrent on the circle. One sec, guys, I'll be right back. All right, let's see. We want to show AN is tangent. Maybe I should draw in that circle just for the heck of it. So AM is, try moving. So basically, if I move M around, interesting. So yeah, what does that mean? Maybe we could do it. Maybe we could like show by the radical axis theorem BKCL and the tangent at A are concurrent. I feel like it might be easier to turn this into like a concurrency problem. Is BK on some kind of a circle? Not sure. All right, so there's more information here. So yeah, BMK is isosceles. MCL is isosceles. What if I drew this circle? Yeah, we have two isosceles triangles like this. And so angle ABM is equal to angle CBK, right? Maybe it's worth extending CM to meet the circle. And maybe it's worth extending both CM and BM to meet the circle. Not sure. This is hard. Hey, Sai, thanks for joining. We're doing a pretty tricky problem here. We just started it.
Hey, how's it going?
Good.
So what is the problem? If you can explain it in 1 to 3 minutes, that would be good.
Yeah, so we have a triangle ABC, and then we draw the parallel through A to BC, and we pick a point M on that parallel line. And then we draw the perpendiculars to BI and CI, where I is the incenter. So D and E are the perpendiculars from M to BI and CI. And then, we reflect M about BI and CI. So I drew the perpendiculars in later, but if we reflect M across BI, we get K. If we reflect M across CI, we get L. And then if you let BK and CL meet at N, we want to show AN is tangent to the circumcircle. All right. What if I think it might be easier to do this. What if I let the tangent at A meet BK at a point, I don't know, N prime, let's say. So and then I let CL meet that tangent at N double prime. And I want to show BN prime is BN double prime.
I think I have got this. M and N are orthogonal conjugates of each other.
What are isogonal conjugates?
This means that
I know what isogonal conjugates are, but
M and N with respect to ABC.
Okay.
So angle MAC equal to angle NAB, which is angle C.
Angle MBA is equal to angle KBC, right? Are you saying K and L are isogonal conjugates?
No, I am saying that M and N are isogonal conjugates.
Because M and N. Okay.
And yeah, this kills it.
All right. So I see angle MAC is equal, or we want to show is equal to angle NAB, right? And then we also want to show, they are isogonal conjugates, yeah. So if we let BK intersect the tangent line at N, then M and N are isogonal conjugates. And the same would be true if CL intersects BK at a point. And so they have to be the same point. That's brilliant. I love it. Thanks for the solution.
Yeah, in center, Kinda hinted that you need something about angles.
All right. So, but I did use the in center in proving that they're isogonal conjugates. So I'm going to write this out. So let the tangent I love that solution. All right. We want to let it meet BK at N prime. All right. And then angle MAC is equal to angle ACB. So we have angle MAC is equal to angle ACB, which is equal to angle N prime AB. And also we have, what was it? We wanted to show okay, so they make the same angles with angle A, and then we want to show they also make the same angles with respect to angle B, but that's true because we have angle MBA is equal to angle IBA minus angle IBM, which is equal to angle IBC minus angle IBK, which is equal to angle KBC. And that's so if angle MBA is equal to angle KBC, which, I mean, that's 180 minus angle M prime BC. Whoops. There we go. So basically, M and N prime are isogonal conjugates with respect to the triangle. Because if angle MAC is equal to N prime AB and MBA is KBC, and basically KB is the same ray as N prime B. So M and N, like basically the directed, if we're using directed angles, the directed angle N prime BC is basically equal to like the directed angle MBA, mod 180. So basically M and N prime are isogonal conjugates, or I'll say N prime is the isogonal conjugate of M with respect to the triangle ABC. And similarly, if N double prime is the, actually, let me write it like this. Let the tangent line plot L. So similarly, if L is the intersection, if N double prime is the intersection of L with with CL, then N double prime is the isogonal conjugate of N with respect to triangle ABC. So that means that N double prime is equal to N prime. We'll do this. All right. So that means that N prime equals N double prime equals N. All right. Very nice. So I will move on to the next problem. Yeah, I liked how we use isogonal conjugates. I feel like I haven't used that in a while on my channel. But does it make sense to everyone?
Yeah, very neat.
All right. So I'm going to move on to the next problem.
Let's also follow from sine law form of Siva.
Oh, it also follows using trig-Cheva?
Yeah.
Well, yeah, actually, you can prove isogonal conjugates using trig-Cheva. So yeah, I would kind of expect that would work. That's a good point. All right. So here's the next problem. So we have a cyclic quadrilateral. A, B, C, D. E is the intersection of A, B, and C, D. F is the intersection of AD and BC. Okay, let's make it look nice. Something like this. So we have, this is a very, common configuration with the Kel point and all that. So here's E. This is F. I is the intersection of AC and BD. And this, so that's I. And then the circumcircles of FAB. Okay, so these are going to intersect at the McKell point, right? So circumcircles of FAB and FCB, they meet at the McKell point of that quadrilateral, so that lies on EF. And those circles, okay, then we draw the line FI, and it meets the two circles at K and L, so it meets the circle. So FAB, it meets it at K, and the other circle meets it at L, and we want to show EK is equal to EL. I don't know if this is like trivial using Ricard's theorem or something, or if it's like a harder theorem, but it might be easy. I don't know. Okay, so, oh, whoops, I hit L. We want to show EK is equal to EL. Let me try to make it so K and L don't look so close to the line. Actually, I think this might be like the best picture we can get, really. So I guess we want to show that. This kind of feels a little bit like the power ratio lemma, to be honest, because if we take the midpoint of KL, we want to show EH is perpendicular to KL. And if we take the midpoint of it feels a little bit like the power ratio lemma, to be honest.
By the way, is EK tangent to the circle AKGF?
Wait, hold on one sec. So if we take those three midpoints, I think J, H, M, and G are cyclic. J, H, M, G, and C are, yeah. So I think this, I wonder if this solves the problem. But what were you going to say?
Why they're cyclic? Why do you think they're cyclic?
Because basically the power ratio lemma says that, so we have the circles FCD and FAB. And if we take the midpoints of AD, if we take the midpoints of the segments connecting the corresponding, like, so F, D, and A are
similar. So the similarity makes them, what can I say?
Yeah, I think you get it. I'm going to write out the proof formally, but
right.
Yeah, because FCD and FAB are similar, and like M and J are kind of like halfway between. But and H is also halfway between. So yeah, I think, let me see. Once we know that this is cyclic, can we show that EH is perpendicular to JK? Is it a pole and polar kind of idea? Let's see. So
by the way, can you just check that is EK tangent to AKGF.
AKE.
GF. Yeah,
AK. I'm sorry. Did you say KDF? No.
no, circle which is already drawn, ABF.
ADF.
Yeah.
So
EK
you want
should be
EK should be tangent. Oh, you're saying EK should be tangent to the circle. Yeah. Yes.
yeah. If both of them are tangent, then we are done by power of point.
Yeah, because E has the same power with respect to those two circles. So yeah, if we can show their tangent, I think showing their actually, I don't even think we needed these midpoints right here. I think it's just true by Ricard's theorem because I think we can show that Fi is the polar of E. Yeah, if Fi is the polar of E, then it passes through the two points of tangency. Oh, wait, maybe it's not that easy. No, by Ricard's theorem, I think we can show En is tangent to ABCD. And we can also show, okay, so yeah, basically Ricard's theorem so I can show En is equal to EO. I have to show EK is equal to EL. Interesting.
Aren't we done like, because we know that I lies on the polar of E, and if we know that the point N also lies there, then Ni should be a straight line, and so K should also lie on the polar of E.
Yeah, so O, K, L, and N all lie on the polar of E with respect to A, B, C, D, right?
Yeah, that's by
Ricard's theorem. Yeah. We want to show, so I can show O and N are on the polar of E with respect to this circle. We want to show K is on the polar of E with respect to this other circle, ABGF. So
yeah, we see that En and EO are tangents.
Yeah, En and EO are tangents. I agree with that. So En is equal to EO, and we have to show EK is equal to EL, right?
Yeah.
All right.
Yeah, we also know that F, we know something about F from the Brocard side, I guess.
So I think...
Let me, with a pen and paper, give me a second, please.
Okay. Are A, M, and let's see. Yeah, so yeah, can we show EK is tangent to the circle? Let's see. So we want to show EH is perpendicular. Let's see. Is it clear that EH and J are collinear? Actually, I think this might just be true. Yeah, by the power ratio lemma. I'm just thinking it through. Yeah, basically, I think we can show the midpoint of KL is the same as the midpoint of ON. And I think that solves it. Because by the power ratio lemma, the midpoint of KL is cyclic with J, F, and G. And yeah, this is true basically by the power ratio lemma. So I'm going to write out the proof. Actually, and I don't think we need point M. Oh, 80 is not necessarily a diameter, sorry. But I still think, I kept thinking 80 is a diameter, but I think the proof still works. Oh, AH and J aren't, EH and J aren't necessarily collinear. I got tripped there. Let me check this. I don't think this is necessarily 90 degrees. Yeah, it's not. Okay, it's not as easy as I thought. Oh, wait a sec. So yeah, we have all the McKell circles, right? That's cyclic. Yeah, let me make this not look like AD is a diameter. All right. I think that's better. Kind of like this picture. Hey, Hakan, thanks for joining. So yeah, I feel like this problem feels like there should be a way to solve it using like just projective geometry, although it's not totally trivial. So yeah, I wonder if Raffaello, maybe he lost his connection or maybe he just had to leave. But thanks for joining, Hakan. All right, so we want to show EK is equal to EL. We know EO is equal to EN. Yeah, so I think all I have to do so if H is the midpoint of ON and M is the midpoint of BC and J is the midpoint of AB, can I show JHMF is cyclic? It feels like it should be simple idea. I think I can. Hold on just a sec. Yeah, okay, there's a very simple thing that I want to show. Let me try something. Like I wonder, yeah. Okay, I feel like I've reduced it to something that feels pretty simple, and now I'm just trying to show that. Yeah, if we can show J, H, M, G, and F are cyclic, that would solve it, where J is the midpoint of AB, H is the midpoint of ON. So I think it might, I just don't remember exactly how. So yeah, J is the midpoint of AB. Okay, one sec. Whoops. Oh, wrong circle. Okay. breakout. Oh, yeah, okay. Yeah, no, that's very simple. Okay, so, all right. So that solves the problem. And I think are PI and G also collinear? I think that's a property of the configuration. Yeah. Okay, so that's all part of McKell theory. Okay, so I'm going to delete some of the extra stuff I added, and I'm going to add it in as I do the proof, just so we kind of have an idea. Okay, so we can delete, so yeah, did we need O and N? Yeah, basically I showed the midpoint of ON is the same as the midpoint of KL. So that's kind of how I solved the problem. Okay, so I added in a bunch of points here. So by Ricard's polar theorem, IF is the polar of P with respect to the circle ABCD. And that implies that IF passes through N and O. All right, so that's Ricard's theorem. And add in, I wonder if I even need the McKell point actually for the solution. I don't think I do. All right. So let M be the midpoint of BC, J be the midpoint of AD. And H, we want to let H be the midpoint of ON. All right. So, and P be the center of ABCD. All right. So angle PJF equals PHF, which is equal to PMF. So that's a cyclic quadrilateral. So angle PJF equals PHF equals PMF. So PJHMF is cyclic. Yeah, why didn't that work? Okay. For MHPJF, I'll just write it like that. And then if H prime is the midpoint of KL, then basically by the power ratio lemma, we can show that H prime lies on that same circle. So yeah, so let me check this. Hold on a sec. Yeah, because this would be HL times HF over HK. Oh, I should put H prime. And that's equal to 1. Is that right? Yeah. And then this ratio is the same for what was it? For points M and J. So by the power ratio lemma, basically MH prime JF is cyclic. So that means that H prime equals H. And that means, so ON and KL have the same midpoint. So HK is equal, yeah, if ON and KL have the same midpoint, then EK equals EL. All right, makes sense? See who's on. So yeah, the power ratio lemma. So yeah, basically, if we let H prime be the midpoint of ON, if you take the ratio of the powers with respect to FCB and FAB, it's 1. And the same argument would give 1 for M and J. And so that means all 3 of those points lie on a circle through F. Yes. All right.